Good day, everyone. We're the Group 10 and we'll be presenting PV-based energy conversion and thermoelectric energy conversion. Okay, let's get started. Definition: photovoltaic energy conversion is defined as a process of direct conversion of sunlight into electricity using the photovoltaic. This is achieved within a solar cell, which is fundamentally a semiconductor. The PV process produces a direct one-step path from light energy photons to electrical energy, that is direct current. Distinguishing it from a solar thermal system that first converts light into heat. So this photovoltaic energy conversion converts the light energy, which is those photons or sunlight, it converts into electrical energy, this electricity, okay, under the photovoltaic effect. And this is achieved within a solar cell. I can already see a solar cell already. There's a lot of solar cell. One of them is this calculator. This one has a solar cell, okay, which is essentially a semiconductor, okay. So this is a one path, sunlight to electricity. It cannot go from electricity to sunlight, or if you try to force that, that will be another process. That will be not photovoltaic energy conversion, okay. So this energy produced is DC current, okay, direct current, okay. That is the electricity. Then the underlying principle is the photovoltaic effect, which begins when a light particle or photon is absorbed by the semiconductor materials of the solar cell. For this absorption to occur, the photon's energy must equal or exceed the material's bandgap energy, a specific energy threshold for the semiconductor. If the criterion is met, the absorption process excites an electron from the bound state into the conductor bands where it becomes free to move. So, so if a sunlight hits the semiconductor, let's say the solar cell, and the energy of the sunlight is equal or beyond the band gap energy of this material. Let's say to define this band gap energy, it is the energy amount for the electrons in this solar cell to be knocked off from its shell, becoming free from its shell, okay. So if the sunlight hits this solar cell and its energy is much higher than this band gap energy gap, then it begins to excite an electron, or in case in my term, it knocks off an electrons from the shell. Okay, this bound state, I would rather say is a shell, okay. So it knocks off from the shell and it goes into the conductor band. This conductor band could be a wire, anything that is conductive, and they become free to move. So let's explain it again. For the conversion relies on this photovoltaic effect where if the sunlight hits the solar cell and this energy is more than the band gap energy of this material, it knocks off those electrons from its shell, or in this power point, it excites an electron from its bound state and then goes to the conductor band, which is anything that's conductive, wire, the traces of those PCB, okay, anything like that, and then they become free to move. And then in the principle, in a particular solar cell, this process is centered on a PJ junction, which is formed by joining two types of those semiconductor materials. There are two of them: N-type negative, doped with atoms having 5 outer shell electrons, creating an excess of mobile electrons, and the two P-type positive, doped with atoms having 3 outer shell electrons, resulting in a shortage of electrons, referred to as positive holes. Okay, so in this solar cell, if you try to break it down, there's actually the N-type and the P-type. So this N-type has 5 outer shell electrons, let's say 5 valence electrons, say, and then this P-type has 3 valence electron. Okay, these outer shell electrons can be also be called valence electron. Okay, so this one has excess and this one has shortage, and because this one has a shortage, then it must have a free hole there, and this one electron. So we already know it's gold here based on the physics. The excess electron will try to go to the hole. We will explain it further later on. Okay. Now p-n junction creates a built-in electric field that functions as a separator. This field separates the electron hole pairs generated by the absorbed photons, pushing free electrons to the n side and holes to the p side. This charge separation creates a different voltage across the cell, and when electrical circuits connected, the excess electrons flows as an electrical current. The output P of a single cell is the product of the current and potential difference. Okay, so let's say this one, let's simplify this one, I will teach in visual. So let's say this is the P type, N type and P type. So we all know if negative and positive, this already produce electrical field and this acts as a separator. So it separate this, the electrons and the holes further. It separates. So when the electrons try to go from this N type to this P type, it cannot go because there's a electric field. There's an electric field that acts as a separator. Okay, so when the photons knock off this electrons, it cannot go to this electric field because it's a separator, it acts as a separator, but rather it can go if there's a wire that also goes there, an alternative road. So electrons can go to this conductor band and then it goes to the hole. So this is alone also already potential difference. And this electron is already a current, carries a current, so that produces power, and which is the P is equals to current times voltage. So according to Messenger and Kabhati, these are the components of a PV cell, PV systems. One, PV cell, the smallest basic semiconductor device unit responsible for the direct light to DC electrical conversion. Okay, so this PV cell is the one that does the job of converting sunlight into electricity. And then two PV module, a functional unit constructed from multiple PV cells that are electrically interconnected in series or parallel. The cells are encapsulated within materials, often glass, and secured in a frame for mechanical protection against environmental factors. So this PV module is just a group of PV cells a group of connected PV cells. The configuration could be in series or in parallel depending on what voltage and current is trying to hit, okay, trying to achieve. So example in this calculator, if although you cannot see it from the camera, if I try to look at it, there are four PV cell, and this four PV cell is already one module. So this is already one module, okay? This is one module. One module, four PV cells, okay? And the statement of being encapsulated with materials of in glass is true. There's glass. It's really glass. I can tell from its touch. Okay. Now number three, PV array. This is the complete power generating unit performed by interconnecting multiple PV modules in series or parallel to achieve the total required system voltage and current. So PV array is just a group of connected PV modules. Okay. Either in series or parallel to achieve the desired voltage and current. So if I try to think in a different way, PV array is a group of connected PV modules. PV modules is a group of connected PV cells, and this PV cell is the one who does the conversion. Okay. Now for energy storage, primarily used in a system not connected to the utility grid, batteries store energy for use during the periods of low or no sunlight. So example in this calculator, since there's no sunlight in my room, then this solar cell cannot produce electricity, but rather is the job is now the battery behind this one. Sorry, the battery. This battery is the one is providing voltage to this is providing electricity to this calculator to perform simple action. Okay, but if I am outside of this room, there will be sunlight. Then the ones producing electricity now is this PV. Okay, this PV module, but at the same time it also tries to charge this battery. So when there's no more sunlight, then it's the job of the battery to give electricity to this calculator. And then these are the associated system electronic components in the PV system. So more on electronics. Charge control regulates the flow of DC power from the array to the battery banks, preventing overcharging or deep discharge, which can damage the battery and reduce its lifespan. So, technically means it tries to maintain the optimal level of this battery, okay? To not, you know, do not reduce its lifespan, to lengthen its lifespan, not really lengthen, but rather slows down the reduction of its lifespan. Okay, trying to slow down the aging of this battery. And overcharging and discharging also damages the battery. So that's the job of the charge controller. It regulates the flow of DC. And let's say, oh no, this battery is already at 60%. Okay, let's try to. Let's say that 90 to 100%. That means overcharging up, and 0 to 10% is the deep discharging. Let's say this battery has 60, so it's near to that overcharging. So the charge controller will limit that flow of DC. So let's try to charge slowly so it will not actually go to overcharge. And when it actually reaches 90, then that's the job of the charge controller to not give that battery a electricity, okay? Not give DC. Again, if the battery is already at 30%, so it's near the 0 to 10%, the discharging, then the charge controller will actually increases the DC, not not to the not beyond the maximum, okay? Maximum voltage of this battery increases to prevent going to 10%. So essentially, it slows down the aging of the battery. So that's the job of the charge controller. The inverter devices that performs the critical function of converting the direct current DC power produced by the PV array into standard alternating current power used by most residential and commercial loads. Of course, we let's say we have solar panels to produce electricity to be used in appliances in our homes, like refrigerator, microwave, and many more. But these things uses AC, not DC. And that's the job of the inverter to convert the generated electricity from the solar panels, which is DC, to AC, which we can use it in our appliances in our homes. Okay? Now the maximum power point trackers, specialized electronic circuits that continuously adjust the PV array's operating voltage and ensure it delivers the absolute maximum power under continual charging condition. Okay, so of course the produced voltage by the solar panel is not fixed, unlike those variable power supply. You can adjust, like I want 15 volts, then I only produce 15 volts. This one, it depends on the conditions. If it's cloudy, of course it will produce less voltage, because cloudy means less sunlight, and less sunlight, less electricity. Okay, and that's the job of that maximum power point trackers. So it analyzes those conditions. It continually adjusts depending on the conditions, the environmental condition, and it adjusts accordingly them, and to ensure that it produces the maximum possible powers. Okay, so yeah, this maximum power trackers really depends on this environment. Okay. So that's the job of the maximum PowerPoint trackers. It continuously adjusts the voltage to deliver the absolute maximum possible power. Remember, the power is current times voltage. Okay, that's it. Those are the associated system electronic components in the PV system.
Good day everyone, I'm Kaisel Misakipit and I'll be reporting photovoltaic system types. The first type is the off-grid system. In off-grid systems, also known as standalone systems, are designed to operate independent of the electric utility grid and generally designed and sized to supply certain DC and AC electrical loads. Off-grid systems require a battery bank to store the energy your panels produce. They are often paired with a generator to provide backup during the long stretches without sunlight. The second type is the on-grid system. The on-grid system, also known as grid tie, or grid feed system consists of the solar panels, the inverter, meter, and the power or utility grid. They are connected to the grid through inverters and do not require batteries because the grid can accept all of the electricity that a PV generator can supply. Alternatively, they are used as power stations. Third is the hybrid system. Hybrid system consists of the combination of on-grid and off-grid solar power systems. The storage of power through batteries for use at any time, without consuming it from electricity grid makes the system convenient to use and reduces the electricity cost. Advantages and disadvantages of photovoltaic system. Photovoltaic systems are still highly reliable even under harsh conditions. Photovoltaic arrays ensure continuous and uninterrupted operation of critical power supplies. Strong persistence. Most modules in a previous system have warranty period of up to 25 years and remain operational even after many years. Low maintenance. Photovoltaic systems require only regular inspection and occasional repairs, which are extremely low cost compared to conventional fuel systems. Zero fuel consumption. Photovoltaic systems do not require fuel and can eliminate associated procurement, storage, and transportation costs. Strong security. Photovoltaic systems do not require fuel and can be safely operated after proper design and installation. The disadvantages of photovoltaic systems. It has high startup costs. Each PV installation should be economically evaluated and compared to existing alternatives. At present, the construction cost of photovoltaic system is relatively high, but with the reduction of photovoltaic system construction costs and the rise of traditional energy prices, photovoltaic system will have strong economic competitiveness. Available solar radiation instability. For any solar system, weather changes will greatly affect the amount of electrical energy output. Therefore, the system design needs to be adjusted according to changes in climate and location. Have energy storage requirements. Some photovoltaic systems use battery as energy storage devices. This increases the footprint, cost, and complexity of the system. Efficiency needs to be improved. In order for PV system to reflect cost effectiveness, we need to use an efficient method to distribute the energy generated during use. However, they are now often used to power alternative inefficient appliances. Lack of knowledge and skills. Photovoltaic technology is an emerging technology. The lack of relevant information limits the development of its market and technologies. Application of photovoltaic systems. Residential power generation. Many homeowners opt for social PV to power their homes. These systems not only reduce electricity bills but also provide backup during power outages. Commercial and industrial usage. Businesses and factories are adopting solar technology to meet their energy needs sustainably. Large-scale installation help offset energy costs and contribute to environmental goals. Floating solar panels. An emerging trend is the use of floating solar panels, which are installed on water bodies such as reservoirs, lakes, and ponds. These setups save land spaces and improve panel efficiency due to the cooling effect of water. Rural electrification. In areas where grid connectivity is limited, solar PV applications provide an effective solution to power remote communities. Agricultural use. Farmers are turning to solar PV systems to power water pumps and other equipments, ensuring cost-effective and reliable energy for their operations.
Good day, everyone. I am Daniel M. Benedilio, and I will be discussing the thermoelectric energy. So, a thermoelectric conversion is the direct transformation of heat temperature difference into electrical energy and vice versa. This simply means that if one side of the device is hot and the other side is cold, it automatically creates electricity. And if for example I do the opposite, like if I give it electricity, it can move heat, so it can work as a generator or a cooler. In practice, a thermoelectric device or generator or cooler produces a voltage when one side is hot and the other side is cold. You can imagine it like this: when one side heat ups, the particle inside start moving faster and push the electric charge. That push becomes voltage. So the bigger the temperature difference, the more electricity it creates. These solid states devices have no moving parts, silent and reliable. Since nothing inside is spinning or rotating, there's nothing that wears out. That's why they're used in places where you need long-lasting, low-maintenance power, like in space. And they can also be used for power generation, cooling, or temperature sensing. Principles: the Seebeck effect. V is equals to alpha times delta T. This formula is just saying that the voltage depends on the temperature difference. If the hot side gets hotter, the voltage goes up. If both sides are at the same temperature, the voltage is zero. Peltier effect. Current through junction moves heat between sides. Actually, this is the opposite of the Seebeck effect. Instead of heat creating electricity, electricity moves heat. So for example, if I apply current, one side becomes hot and the other side becomes cold. And that's how mini fridges and CPU coolers using Peltier plates work. Performance metric. Figure of merit Zt is equals to S squared sigma T over K or kappa. Higher Zt is equals to better for performance. Low Zt is equals to weak performance. Zt is just a score that tells us if a material is good for thermoelectrics. Components: thermoelectric module. Many paired p-type and n-type semiconductors legs are arranged electrically in series and thermally in parallel. These little legs, like the p-type and the n-type blocks, are where the magic happens. Each pair makes a tiny amount of electricity, but when you connect many pairs together, the voltage adds up. Thermal interfaces and heat exchangers. Heat source from the hot side and heat sink from the cold side with thermal interface material or TIM and fins or water cooling to maintain delta T. These are the parts that keep one side hot and the other side cold, like for example, a heat sink, cooling fins, thermal paste. Without a good temperature difference, the device won't work at all. Electrical interconnects or power conditioning. Wires and converters that route and regulate the generated electricity. These are just the wires and circuits that carry the electricity out of the module. Sometimes the voltage is small, so the converters are used to boost or stabilize it. And from the image from the top right, as you can see, the P is just the P-type leg and the N is the N-type leg. Heat enters from the bottom side, which is the hot side, goes through the legs and exit at the top side, which is the cold side. As the heat flows upward, electricity charge move and create voltage. And the zigzag there, like the metal lines, shows how legs are connected in series so that the voltage adds up. So this basically is just many tiny heat powered batteries are connected together. Applications: waste heat recovery. Capture vehicles or industrial exhaust heat to generate auxiliary electricity. These devices can sit on hot pipes or exhaust system and convert leftover heat into small amount of electricity. It's not a huge power, but it saves energy that would otherwise be wasted. Space and remote power. Reducible thermoelectric generators or RTGS and long life remote sensors or no moving parts reliable. Like the spacecraft, it uses thermoelectric generators powered by heat from radioactive materials. No moving parts means it can last for decades without maintenance. Cooling and spot refrigeration. Peltier modules for portable coolers and electronic spot cooling. Peltier plates can cool small objects like CPU, sensors, or mini fridges. They're great when you need quiet and compact cooling. And these uses are proven but limited by modest practical efficiencies. The only downside is that they're not very efficient, but researchers are working to improve materials so they become more practical in the bigger system, as the ongoing research focuses on improving ZT and thermal management. That's all, thank you. Here is our references. Goodbye.